Hello everybody, my name is Justin Carpentier and today I will introduce you our work on proximal and sparse resolution of constraint dynamic equations. So constraint dynamic is an important topic in robotics as many robots may suffer from contact interaction or might have loop constraints that are hard to handle in simulation. So constraint dynamics follows the so-called least action principle, which states that the current joint acceleration should be equal to the free acceleration of the system according to a kinetic metric here, while also enforcing the contact constraint acceleration. So in particular, to derive the solution of this constraint optimization problem, one needs to introduce the so-called Lagrangian of the problem, which is composed of the cost function together with the equality constraints, and add an extra variable which corresponds to the so-called dual variable, which are nothing more than the contact forces in our setting. In particular, by deriving the so-called KKT conditions, one can retrieve the so-called KKT dynamics with here the unknown quantities that we aim to retrieve, and here on the left we have the so-called KKT matrix, which accounts for both the joint space inertia matrix and the constraint Jacobian here. According to the rank of this constraint Jacobian, this problem might have one solution, redundant solution, or no solution at all, meaning that the KKT matrix here is not always invertible. To make the problem always well posed, we propose to add an extra term to the Lagrangian of the problem, here by adding this strongly concave function in the contact forces, which is called the proximal method of multipliers. And so by doing so, we have the strong benefit of making the KKT dynamics always well posed. This is particularly due to the fact that here we have an extra term which makes the matrices here always invertible. And so by iteratively solving this set of equations, one can show that this problem is converging towards the original solution of the problem. In particular, the problem here is converging towards the least constraint solution if the problem is not feasible. One can adjust the rate of convergence of this iterative process by adjusting the value of mu as depicted by this graph here. In addition to the well-posedness of the problem, we aim also at exploiting at best the sparsity which is inherent to the KKT matrix. And for that, we take inspiration from the work of Roy Feresten in his book Rigid Body Dynamics Algorithm, where he introduced an efficient approach to compute the Cholesky decomposition of the joint space inertia matrix, which has a strong benefit of preserving the sparsity pattern of the kinematic structure. So in order to have this analogy, we need to rearrange the term in the KKT matrices as follows. And we have introduced a new Cholesky decomposition algorithm, which both provides the decomposition of the joint space inertia matrix here, and also accounts for the sparsity pattern of the joint constraint Jacobian. In particular, this algorithm is very efficient, and it has a complexity which is critic both in terms of number of bodies and number of constraints. We notably apply this proximal algorithm framework together with the sparsity decomposition in the context of forward simulation of various robots going from the Solo robot and the Talos robot, and we compare our approach against the state-of-the-art approach proposed 10 years ago by Roy Feresten, depicted here in green, and in a round, this is our approach. In particular, from this experiment, one can observe that our approach is up to 3 times faster than the previous approaches of the state-of-the-art. This is notably due to the fact that we are better exploiting the inherent sparsity of the problem. In addition, here we show some experimental simulation over different constraint sets like 3D context set, 6D constraints, and loop closure constraints. We have implemented all this algorithm within our efficient framework called Pinocchio, which is both open source and freely accessible. And now, for me, it's very time to thank you very much for your attention.